Unit 3, essay question number 3. So we'll talk about a couple different things here. The first thing I want to talk about is how calcium affects muscle contraction. So calcium enters the cardiomyocyte cells and the autorhythmic cells of the heart in a similar fashion, where it's coming through its gated or voltage gated channels here that open up as contraction begins, as it reaches its peak on its action potential graph. And as calcium enters through these channels, we have it hitting a ryanodine receptor, which is right here, which is attached to the SR, the sarcoplasmic rectilium. When that calcium reaches the ryanodine receptor and it binds to it, it opens up that receptor and it opens a gate. That gate will then flood the cell with calcium. Calcium causes muscle contraction. If there was a sarcomere here, this is a very simplified sarcomere, calcium would start to bind onto its sites, and it would cause this to contract, cause the sarcomere to contract, which is in the heart. After calcium has been flooded into the cell, there's two ways for it. The first is that it's going to go back into the sarcoplasmic rectilium to be used again. And there's also a little channel over here called the sodium calcium exchange channel, the NCX channel. And that channel will help regulate calcium amounts if it's all not uptaken by these Circa pumps, which are on the outside of the sarcoplasmic rectilium to reuptake the calcium. Now that we know how calcium works, and this is also all happening in this T-tubule here on all cardiac cells. Now that we know how that works, we are going to talk about inotropy, lusitropy, and chronotropy, and their actions when they deal with norepinephrine and acetylcholine on the heart. So first, just quick definitions. We'll do inotropy and lusitropy kind of together. So inotropy is about the contraction strength, and lusitropy is about the relaxation rate. This inotropy, because it has to do with contraction, really loves calcium, but the lusitropy does not love calcium because it wants to relax faster. So I kind of drew a few things over here. Increased calcium, increased contraction. Decreased calcium is decreased contraction, and the same thing for lusitropy, where you increase the calcium and it will contract or will relax faster, which causes the contraction to go faster. So we're going to follow this flowchart and describe a few different things that happens. So it all starts with stimulation of the beta-1 adrenergic receptor, where it can then activate the this alpha subunit. This alpha subunit goes over to another side piece, and we'll talk about that in a second. So after that alpha subunit is activated, it will increase the adenylyl cyclase in the cell, which increases the cyclic AMP, which will then increase this protein kinase A, also known as PKA. This PKA will do 4 different types of phosphorylation. So the first on this left side is the phosphorylation of the L-type calcium channels, right here. When those are phosphorylated, they open the probability of calcium channels more and more, which then gives us the more calcium influx, increases the concentration of the calcium, and that increase of concentration will affect the release of calcium from the SR, which will give us a strong contraction, which is an inotropic effect. If we come back up here and we phosphorylate the ryanodine receptor, it will dissociate the castalbin 2 from the RYR, which then opens the probability of the RYR receptor more, which then, where we meet up again for the same thing, increases the release of calcium from the SR, increases the concentration, and that will cause an inotropic effect, which is contraction of the heart muscle. Here, if we phosphorylate the phospholambdin, we increase the circa pump use in the 2A cell, which will cause calcium reuptake into the SR to be increased, which increases the calcium stores. The speed of relaxation will increase, which is the lusitropic effect, which will then decrease the duration of the contraction. Because we increase the rate of the relaxation, the entire length of contraction is slower. And then finally, for the phosphorylation, if we phosphorylate troponin 1, we increase the rate of calcium from troponin C, which will then speed up the relaxation again, which is that same lusitropic effect, and that will decrease the contraction. And if we go back up here where we activated that alpha subunit, there's this second option that happens. So the interaction of the alpha subunit with the L-type calcium channels will occur, which will open the probability of these calcium channels more and more, which increases the influx and increases the concentration. That calcium induced release from the SR will increase, and that is another inotropic effect of contractility in the heart. Then finally, if we talk about chronotropy, which is the fancy words to affect the heart rate, we have a positive and a negative effect. So the positive effect is the stimulation of that same beta-1 adrenergic receptor, and it starts the exact same way. We increase the adenylyl cyclase, which increases the CAMP, and in this case it's the HCN or funny channels. Then we'll follow this pathway first, where we increase the sodium influx, and then we start to decay the membrane potential quicker, which means to make it go away, which will increase our heart rate. But at the funny channels, when we increase the PKA, the protein kinase A, we have two things that can happen. First, the calcium influx will increase, and it will either increase the steepness of the slope, which will increase your heart rate of the inotropic lines, or it will bring the negative or the threshold lower so that you can reach that action potential faster, which will increase that heart rate. For the negative side, this deals with acetylcholine at the M2 receptor. So first we have a beta and gamma heterodimer that will open the GERK channels quicker, which will create a more negative membrane potential, which lowers the heart rate, which is the exact opposite of this here in the positive beta-1 adrenergic reception. We have this M2 receptor can activate the alpha subunits, which will decrease CAMP and will decrease the funny channel, which is represented by this IF, and that starts to flatten your slope down, which will decrease your heart rate. And then finally, there's another alpha subunit that we can activate that decreases the CAMP, and this one will decrease the calcium channels, which will make your threshold more positive and harder to reach, which will decrease your heart rate. So if you notice, these two are near exact opposites of each other. They do completely opposite things, which makes sense because of the beta-1 and M2 reception that they receive. Finally, I just wanted to make sure we understand that, like I just said, between the muscarinic and beta receptors, this muscarinic receptor affects the acetylcholine and it decreases heart rate, contraction, conduction, and relaxation. And then the norepinephrine that's affected by the beta-1 reception will increase the heart rate, contraction, conduction, and relaxation of the heart muscles. But that is inotropy, lusitropy, and chronotropy, and how calcium affects the contractility of the heart.